Hi, welcome to my YouTube channel. My name is Mark Bobby Chibuzo, and I will be starting a new series about blockchain engineering with Rust. I would like to just explain what I'm trying to do. I know there are contents out there, but this is just me um, relearning, reviewing in the open. So I've been in the blockchain space since 2021, and I have been in the Ethereum, Cosmos, and Solana spaces mostly. But now I want to like properly prepare myself, go back to the foundational principles about blockchain engineering, and then afterwards I want to come back to the space when I'm done with all of these learnings so that I can um, be properly positioned for the upcoming bull run. And I'm sure you'd want to do the same too. So let's learn together. Right. So I'll be using this link, this guide from roadmap.sh to um, structure my learning, and hopefully your learning too. So I will be starting from this. So the blockchain space has seen a lot of like growth, movements, evolution, and all of that. And while they've been scaling and growing and everything, it still follows this fundamental structure. So once you are very well grounded in the foundational stuff, you will probably have little to no problems um, with whatever is currently ongoing in the space right now. So um, yeah, what is the blockchain? Before I go into the definition, we will definitely be doing a lot of like programming, like real practical programming to solidify whatever we've learned into our brains. So we're using Rust where it matters. But if situation rises where we have to use another language like Solidity, Golang, TypeScript, whichever, we will quickly switch, because we are trying to be blockchain engineers, not Rust engineers or something. So now, what is the blockchain? From definition, the blockchain is just a chain of blocks. I have written an article here, and inside of here, I explain the blockchain is just a chain of blocks, and every single block is connected to the one before it and the one after it, right? The most official definition I have is the one from Wikipedia about blockchain, this one. And what does it say? It basically says that a blockchain is a distributed ledger with growing list of records called blocks that are securely linked together via cryptographic hashes. So it is a distributed ledger. First of all, what is a ledger? A ledger is basically um, a record, right? Like it rightly says, it is basically a record. So it means that you have um, probably contact list record. It could be transactions, financial activity record, and all of that. But it's a record, a ledger. So the difference now, like the next thing now rather, is the distributed. What does a distributed ledger mean? It means that instead of having your contact list saved only to your phone, you have it on your cloud, you have it on Microsoft cloud, you have it everywhere. You have it on your second phone, your laptop, and everything. So that is what it means to be distributed. It means that instead of having something in one place, you have it in multiple places. Now, the benefits of distribution and how it differs from the normal simple way of just having it on your phone is that when something is distributed, then it doesn't have a single point of failure. So, for example, you have your contact list on your phone. What happens if your phone gets spoiled or lost or stolen or something? That all your contacts are gone. So you must have it up. You must have it backed up somewhere. But the difference between this distributed of backing up somewhere and then keeping redundant copies of an existing server or something with the with distributedness, like with decentralization, which is one of the benefits of blockchain technology. The difference is that decentralization doesn't mean it doesn't like while where distributed means having copies where those copies are probably working or not, mostly not. Decentralization forces like it mandates that the copies are working at the moment and they are up to date in not just as a replacement, but they are actual working instances of that ledger. So yeah, it means that you can use your laptop to make call with those contacts directly, not just your phone. So basically, like having two phones. That is what decentralization actually means. So um, so they are secured. These blocks, these records are secured, and they are linked together first of all, and secured via a cryptographic hash. So each block contains a cryptographic hash of the previous block. It contains a timestamp and the transaction data that is generally represented as a Merkle tree, where data nodes are represented by leaves. Recap what that means in easier terms. It means that the block, a particular block, right? It contains a cryptographic hash. I think it's better to so while I was writing the article, I had to like sit down and design some pictures, some media visual content for it. So this is a block. This entire rectangle is a block that lives on the blockchain, right? And the very first block that ever makes it to the blockchain is called the Genesis block. Now it is unique because it is the first, right? And one of the uniqueness is that you could put literally any information on it depending on what you want to be there, right? It is not a fixed block of information. You decide what you want to put there. It will be compatible with everything else, right? But it will be unique. So one of the most obvious uniqueness is that since it is the very first block, it means that there is no block before it, right? So this the property. So we have elements, right, of each block. A block is like a bag; it holds a lot of things in it. So the Genesis block, as well as every other block, contains something very um, generic amongst other things. The elements, and these elements include the timestamp, the time that that block was being produced, um, the previous block hash, right? Because that's how they are linked. Then its own block hash, its current block hash, right? Then it contains a nonce. For now, we're just going to reason a nonce being an index, right? So this is block number one. This is block number two. And the reason we are using index is because when we start programming, we want that ease in the sense of an index is something that does not repeat. So in an array, you must always have 0, 1, 2, 3, 4, 5, and on. You can never have 0, 1, 2, 1, 2, 3, 1 like that. No, it's not possible. So repetition of each block is impossible. So that is what an index is. The reason is because the previous block before it and its current block contains data that that block itself can like data that cannot be in any other block, right? So I'll try to make it more explanatory, but you will understand better when we start like programming this out. So that is what a block contains. It also contains transaction data, and um, a difficulty along with the nonce. So these nonce and difficulty, there are things I remove the difficulty because it depends on the consensus protocol that the blockchain uses. I will stop overwhelming you at this point and I'll just move back here. So each block contains a cryptographic hash of the previous block. Now that means that this hash this hash. This is the current block, right? The first block. And then we hash some things from it, from the elements, right? And then we send that hash to the next block. So the block is a very important part of this new brewing block. Brewing, Brewing, right? So a big part of this brewing block is a pointer, a hash of the previous block. If there is none or if it's incorrect, then there's like it's a breakout. It's not possible. So yeah, um, um, the transaction data. It's one other unique part. So the block, the content of the block is being broken into two: the block header and the transaction body. So the block header contains every single thing else here you're seeing, right? Aside from the transaction data. It is the only unique changeable thing. So the transaction data usually contains a sender address because it's a transaction. It means something, money, value going from one person to another. So it contains this an address. On Ethereum, it is OX stuff, right? But we're just going to put Alice here. And then the amount being sent, right? And then the recipient. And it's going to be multiple of that. So you could have like transactions like this ongoing, right? So um these parts, it's different. Like I'm just being lazy, that's why I haven't. But the way I edited every single field, I'm supposed to edit all of these too. So that is what a block is made up of, right? So it will make more sense when we start like writing the foundational aspect of the blockchain. But um, the header, everything that makes up the block header, which is everything aside from the transaction body, is being hashed by a technology called Merkle tree. So the way it works is uh, all of these things are very very important. And if you look at the way Wikipedia, this is a Merkle tree. It's also called a hash tree. This is how it looks like, right? We have at the bottom here, we have data blocks, right? We have four transactions here, basically, right? And then these four transactions, they are being fetched, and each of them are being hashed. Then after they are being hashed, their resulting hashes are being hashed here, right? And then the same happens in these other parts. And then the resulting hash and the resulting hash from these other parts, they are both hashed to get a final hash. So you just keep hashing until you have just one hash remaining. That is how Merkle trees work in a nutshell. So we use the Merkle tree technology to hash the transaction data, and then we use maybe SHA-256 or any other hashing algorithm to hash the block header, right? So, but I mean, you could do anything you want. You could use both. You could whichever. But this is like the very very best the best way. So I have actually like sat down and built a blockchain from scratch twice in Golang, and that is why I'm using Rust for this third time. And I because I want to strengthen my Rust skills. So we've seen everything about this now, right? We'll be moving to the next line, which is it contains a cryptographic hash of basically everything that makes up of the um, block header and the transaction data, generally presented as a Merkle tree. The transaction data represented as a Merkle tree, where all data nodes, all transaction data nodes are leaves, right? So the Merkle tree for the transaction data, and then the rest of this can also actually be the Merkle tree, but you could actually make it easy for you and just use maybe a SHA-256 algorithm. So since each block contains information about the previous block, they effectively form a chain compared to linked list data structures. We might maybe have like another playlist about the data structures, especially the ones that are being used in blockchain, both existing data structures and maybe even um, what are they called? Custom built data structures like sorted key value, and everything else. So with each additional block linking to the ones before it. So there's a link between the very first block and the next block and the upcoming block, all of that, just like we saw here. So just imagine that there is actually like this here, right? Just imagine. Yeah. So they are linked backwards like this. So the next line, consequently, blockchain transactions are irreversible in that once they are recorded, the data in any given block cannot be altered retroactively without altering all subsequent blocks. Right. So what that means is that once this first block, right? Once it's been attached, hashed, and pushed, and then the hash is fetched and sent to the next block. When you are brewing a new block, right? You as long as there is like a new block, you won't be able to change this thing. You won't be able to change anything here. Reason being that the value is already being used here. So if you want to try and attempt changing something here, like the amount being sent or the nonce or maybe the time, uh, you would have to first of all change this block, touch this block. And then when you successfully do that, that is when you would now be able to update this and then commit that new change as a new block. But it is not possible because that would just break everything and that would not be a decentralized blockchain. So um, blockchains are typically managed by peer-to-peer computer network for use as a public distributed ledger, yeah, P2P. So the difference between this a decentralized, and a distributed network is that a centralized network, right? You have one source of truth, one pinpoint, or one point of failure, however it's called. And I think you could liken it to a wrist, right? So when you have like this is a wrist, assuming it's a centralized platform system, it means that this wrist controls the fingers, right? So if this wrist goes off, then you won't be able to control the finger. That's for centralized systems. Then for distributed systems, like we've discussed, it simply means that instead of having one, you're having copies of it, replications of it. So you're having this in a normal Web 2 setting. This is such that if this one goes off, you quickly replace with this one. That is how it is. But in Web3, instead of that, you're having them functioning at the same time, even interacting, exchanging communication. This one goes off, this one is already running. It has already been running, it is up to date and everything. So that is how decentralization works. So, in a sense, we've actually touched what decentralization is. Maybe another time we'll talk about why it matters. So, there is the fact that these nodes, these replications of this particular system, the fact that they communicate with each other, they interact with each other, is the proof that it is a peer-to-peer network system. So the nodes currently they are adhered to consensus algorithms. I think this is tautology. So you could call them consensus mechanisms or consensus protocols or consensus algorithms, whichever. So and these are what they call proof of work, proof of stake, and all of that. What they actually means is they determine how transactions are being validated, who the validators are, how the validators get rewards for the work that they do. So on proof of work, validators mine, and then when the very first person to complete the mine is the person who gets the reward. So that is how proof of work works. I think we might have to implement a proof of work because I believe the proof of stake involves a lot of research that I have not done before now. So yeah, they validate new transaction blocks. That is what the point of a node validator does. Although blockchain records are not unalterable, since blockchain forks are possible, blockchains may be considered secure by design and exemplify a distributed computing system with high BFT. I think that is most of what we can draw from here. So, in a nutshell, what is a blockchain? A blockchain is basically um, a decentralized chain of blocks, right? So, chain of blocks, chain of blocks, chain of blocks, and then they are decentralized. So, you have a laptop, a computer, a server, whichever, that is currently here that has 20 blocks and then it's currently building a new block. And then you can have another one in Frankfurt, for example, that has those 20 blocks and is waiting to fetch the new blocks that is being validated and being brewed by the block that is currently here. So that is how the blockchain is. So you could make a blockchain if you are starting from scratch, for example, you are building a blockchain from scratch for a specific purpose. You could actually make your blockchain to be about anything. It could be about just random payload data instead of transactional transaction data. You could make it about anything. You could make it gasless, whichever way you want it. So the reason that there's gas in blockchains is majorly because we need to compensate validators, node runners, and node providers, and all of that. So that is why, because of the hardware that is being involved in running a blockchain node. So I think with that we are done with the theoretical part. I'm just going to update the status to done and also do the same for this, right? So I might just mark this as in progress because we might be visiting it. So generally, uh, I think it's time for us to just jump on getting our hands dirty so we could like flesh out something, a blockchain, to solidify what we've learned here. And like I said, I'm going to be using Rust and I'm going to be following exactly what we have on that page. So uh, there are still a couple of things we need to review here. But before we come to that, let's let's try to follow this. So I'm going to name it. What's a good name for it? YouTube, Utah. Okay, right. And then I'm going to just seed into it, right? And I'm going to open it with Rust Rover. So I've actually like done this before, and I got I completed the video and everything, but the problem was that I was seeing like 22 gigabytes for the file, and I'm like, okay, if I am going to do this, is it sustainable? Will I continue pushing 22 gigabytes of data on YouTube every time? So that was why I just had to like look for a better alternative and then start afresh. So yeah, that is why my terminal is able to remember all of these commands. So from here, right, they have this. I'm just going to cargo build, no, cargo run actually, right? So it's working, it's set up properly. The very first thing we're going to do is, like it says, we need a block, and we need a chaining for the blocks, and then that forms the blockchain. That's as simple as it is. So we need a block. I'm going to create a new package, or sub create or whatever it's called in Rust. I'm going to call it blockchain, right? And inside of that, I'm going to create a mod file. I could easily just, sorry, I added an R. I could easily just write the code inside of here, but it would not be nice, at least not to me, because it's a blockchain, so it could like blow out of proportion um, before you know it. So just going to do blockchain blocks, right? Blocks, and then inside here, stop, just go. Yeah, and then inside of here, we write what we've known. So what we are doing is create blocks, right? Then create a block, a chain of blocks, right? So these are the two things we are doing. So the very first thing is the block. So pub struct block, right? And we've seen what the block contains. It contains um how do I make this easy to look at? It still remembers. I do think I should turn off. Should I? Nah, I think this 2024, so there's actually no need to turn it off. So yeah, it contains, like I said, we'll be using an index for now until we get to the point where we need to implement the Merkle tree and then the proof of work. So um, the index, I think we don't need that. The index uses the four, just numbers. Then we need the timestamp. It also uses the four. Then we need the transaction data. We are doing a transactional blockchain, so we will just stick with that, right? Then we need the previous block hash. Maybe I'll be able to type faster than it predicts. And then we need the current block hash. So I use string for the most of these things because it is easier to understand for this very first part. So we'll be using for the timestamp. We'll be using time. We'll be using that in Unix epoch, but we'll also be using system time, right? So the very first thing is to implement the block. And what would it get? It would get creating a new block, yeah, and then it would get yeah, generate a hash for the block. I think I find this thing really uncomfortable, but yeah, let's go. So fun, I think we'll just do pub here, new, right? And what would new take? If you're trying to create a new block, what would new take? New we take from here. Is there anything that is what's it called? Similar, something that is here and should be here. Possibly you got it right. The previous block hash, right? So we're going to take an index, right? Just 64, and then we're going to take the previous block. hash, and it's going to be a string. Then we're going to return a block. What is this one doing? I don't think this is correct. Let's just comment it out. So first, we're trying to do two things here. The very first thing we're trying to do is to build a block actually, which is a block. This is what we're trying to return. It must have an index. It must have a timestamp, right? It must have a transaction data, right? It must have the previous block hash and then the current block hash, right? So this tells us that we will be needing a function to hash this value. So while this is fine, we will be adding this function here. So from calculate hash and return is string, just be there for now. So we can start from the top. So the very first is to uh, we pass the index here. So these two guys are actually sorted. So we just need to work on the timestamp. So let the timestamp be actually system time. Pick the now method, right? And then the duration since Unix epoch. Then we unwrap, right? And then we turn this to seconds. So get a U64 and our timestamp is satisfied. What is the next thing to satisfy? The transaction data. So to satisfy the transaction data, uh, we would just add it there, right? It's going to be string for now. Later on, change it, and then we have our current block hash remaining. So I'm just going to delete this. Yeah, and then let's current block hash like this. So what would be good to add to this function as parameter? Just come here. The block hash is a hash of the block header. The block hash is a hash of the block header. And what makes up the block header? Everything aside the transaction data. So we're going to have our index, right? We're going to have our timestamp. We're going to have the previous block hash. So we just add it here. Calculate block hash. Just accept the index, right? The timestamp, the transaction data. We will remove this later on, and then the previous. So I'm just going to put an and here. The reason because they are strings, so we will just put the index. What am I doing? Index U64. I need you to predict now. You don't want to type this whole stuff. So the timestamp should also be a simplistic U64, and then our transaction data we put it like this because it's easier, and then we put, let's do this with txn, and then finally the previous block hash of also. So that has reduced the errors here. So we only have to sort this guy out now. So now to sort this guy out now, what do we do? We can easily just use the cargo, this guy. We can use an MD5, we can use a SHA-2, right? So you're going to make use of SHA-2, this one. I don't think the other ones are actually like out yet. Those other versions, 0.11 and all. So this, yeah, these guys, I don't think they're out yet because the last time I tried using it, I had issues, and then I had to dump down to this one before it worked. So the next thing we're moving back here, and we're going to use SHA-2. Yeah, like this. So we're going to create a harsher. We're going to create a harsher. So um uh this is it actually. This is it actually. So one, two, three, four, five. 1, 2, 3, 4. So just remove the fifth one. And then we are going to do this, right? Oh no, there's no needed string. You could just do this, 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 just to separate them, right? So with that, we've satisfied everything in the create blocks. So we're able to create new blocks, and it's being hashed, right? So the next thing is to create a chain of blocks. And how do we do that? Obstruct blockchain, right? And it's just going to be pub blocks, which is a vec of block like this. And then we can now move to implement. Ah, man, it's really not nice that this thing remembers everything I have written. What am I doing? So yes, so we have the blockchain, and from here, the blockchain is just a chain of block. So we are going to, because we can't just start creating a new block, we have to initialize the blockchain itself. So we just initialize it as one person with that new function you're seeing there. So the very first thing is create a new blockchain, right? And then the next thing is to add a block to the new blockchain. So these are the two basic functions we need for now. So the very first is going to be a public function, new, and what is it going to do? It's going to just accept nothing but return a blockchain, right? So uh, the very first thing we are building a blockchain, so the blockchain, and then it's going to be blocks, and this blocks is going to be vector, right? So this is okay, but we need to add the very first block to this block, this new blockchain. We need to add a genesis block. So we are going to create the genesis, man, the genesis block, and then we are going to make use of this block and call this new. So block new, and you can see what it takes. We're going to start at 0. We're going to call it the genesis block, and this guy just sold me out. Yeah, and then the very final thing is the uh, previous block hash. So because it's the genesis block, we are just going to put 0, 0, 0, 0, 0, 0, 0, 0, yeah, to string, and we've constructed a block. So we're just going to add that genesis block here, and we're good to go. So how do we implement this? Man, this is definitely going to be a public because we'll be calling instead of the main file, like uh like this. Let's not blockchain equals to blockchain blocks blockchain new, right? Then we just go from there and say uh, blockchain.add, yeah, blockchain.add block, right? And it's because we've not, let's see this. Now, so what this actually just did is create the previous block hash, uh, sorry, add block. Add block, you just take the why is that? We are currently increasing the index automatically. So we are not taking it as an input. Then we are fetching this. We are calculating this. We are calculating this. So the only thing dynamic is the transaction data. So yes, this is correct. That is just the value to be in here. So yeah, we access the blockchain and then we get the last block there. So that previous block, um, current block hash becomes the previous block hash of this new block that is being added here. I hope that makes sense. So you're going to push this by just doing a self dot blocks dot push. I'll just push that new block there. Fantastic. So this should pass now. And what does it want? Obviously, it wants a transaction data. So we're just going to let transaction data just be Alice to Bob, Alice to Bob. Yeah, 5 BTC, ETH more like. Yeah, ETH, that's fine. And then we just pass transaction data there, right? And then I'm thinking of doing first, so first, right? And then let's second transaction data go back to let me just get the guys here, J to Sharon. Then if so you're going to repeat this, right? Second transaction data. And then finally we will iterate and then we print out each value like this. You're going to put this. It doesn't work. I think because we need to add the derive debug. I use what's it called now? Roast rover. So I don't really need to come here and make changes. I could just fix it from here. Oh, right. So now let's run it and see the nonsense we have built. Oh, there's a 2x error here. There's a method with a similar name to vec. Quickly jump over there. Nah, this is not what we need. I'm going to make it way easier by us making use of the compute hash by what's it called? MD5. Yeah, we're going to let me just put it there. MD5, right? And then come back here. We will definitely use Shadow 256 in the next video, but for this current use case, we are going to keep it 100 to make it easier by just using our um use MD5. So let's to hash equals to the format this, then we just format, yeah, this compute. So this solves our problem, and we just like generate the blockchain, and you can see it here. The block, the index zero block, timestamp, genesis block, then previous block is zero, current block hash is this. It's hexadecimal as we wanted. Transaction data, Alice to Bob, like that. So index two, index is one, index zero, like that. So that is how a blockchain is built fundamentally. And I'm really very grateful that you watched up to this point. I will be keeping much of these write-ups here. Maybe we might just go through this. So the elements of a blockchain, the nonce, and the difficulty depending on the nature of the consensus mechanism being used. So the nonce is just a number occurring once. It's as unique as this index you're using here. It could also be a UUID. Then the current block hash, the previous block hash, then transactions, and then timestamp. That's the generic element of the blockchain. Then the first block has a set of unique properties. Since it's the very first block, the one of the properties include that it doesn't have a previous block hash of a real significant value. We have coded it as zeros here. Then it could have any kind of content you want it to. Excuse me. So yeah, I mentioned that it could be um the very first day, like the timestamp could actually be the very first day. It could contain metadata for all we know, and then symbolic message. You could embed a message there, whatever you want to do. So next is the my voice is fading. I don't think I've talked so long like this before in a while. So the next thing is the block header. What is the block header? The block header is basically um, the nonce, the current block hash, the previous block hash, and the timestamp combined. So in our next video, we will actually be learning about how to hash the previous block to get the previous block hash, which is a string, and then we use that hash to we add that hash to the newly brewing block, right? So that is how it is going to work. And now I can end this video here, and I promise every single thing, even the articles and everything, will be available on my page when I have like two, three, four. I'm just going to append them here, put them in this place, and then put the proper tag so it's easy for you to find them. Thank you for watching so far, and see you in the next video.